All right, here we go. Sorry. Let's get started. All right. I asked you yesterday at the end of the day, we built this idea of a new function, tangent, all right? If I say cosine, what does cosine find for me? The x value, that's correct. And if we're talking about sine, sine finds the y. And we discovered yesterday that tangent finds y over x, which is the slope. That's correct. Okay? So I asked you to use page 37 in your book to go find these values. Actually, just a second ago, I asked you to go write the angle measure here as well in degrees. What's pi over 6? 30 degrees. All right? You could say pi is 180, so 180 divided by 6 is 30. What's pi over 4? 45. Pi over 3. 60. Pi over 2. 90. Over here, this would be 120, 135, 150, and 180. Okay? So we have that there. Now, I asked you to go fill in this table yesterday. You could use page 37. You could do sine over cosine. And so we did 0 over 1, and you should have gotten 0. It kind of helps you start on that one. All right? So what value did you get for pi over 6? 0.577. Most of us did it that way. All right? I'm ready to begin, guys. All right. What value did you get for pi over 3? 1. Because it was like 0.707 and 0.707 is over the same number on top. This one right here we got 1.73. And on 90 we got undefined. Yeah, so 1 over 0, which is undefined. Okay. If we go over here, what did you notice that happened in this second part of the column? It mirrored it, but what? Negative. But negatives, okay? So this was negative 1.73. This is negative 1. This is negative 0.577. And this was back to 0. Okay? So that's what our table should look like. All right, again, we should have our phones put away. We ought to be working right now up here. Now, I want to go back to this as well. If you look at the chart, many of you got this because you said 0.5 divided by 0.866. You did that all decimal. That's fine. I didn't give you any instruction. Just had you go find that. Now, if I was doing this in exact numbers, it was 1/2 divided by square root of 3 over 2. Those are the two fractions. That was sine over cosine. All right? Well, if I was going to do this, that's a complex fraction. I don't really like the way it looks. Now, there's a good thing about it. The two denominators are both 2's. All right? And so if I did 1/2, I kept that first one, I changed the multiplication, and I flipped the second one, then those 2's are going to cancel. So it's going to leave me 1 over square root of 3. Well, if I were to put 1 over square root of 3 in the calculator, I'd get the 0.577. Okay? If I did 1 was square root of 2 over 2, and square root of 2 over 2, like that. Well, that looks funny, but what is that equal to? 1. It's the same number on top and same number on bottom, so it's good. So that's 1. This one right here is square root of 3 over 2 and 1 over 2. Which again, it would do the same thing it did up here. The 2's would cancel, and it would leave me square root of 3 over 1, which would be square root of 3. And that is the answer for square root of 3. If you put that square root of 3 in the calculator. All right? Now, I'm going back to that, so if they needed exact answers, that's how we could do that. Now, if you remember, I gave you a shortcut on your fingers on how to find sine and cosine. Remember that? Let's go back and revisit it. It's been a little bit. All right? What did the pinky finger stand for? 0 degrees. Ring finger was 30. Middle finger was 45, 60, 90. Okay? I'm going to do 30 with you real quick. So if I were to do 30, I'd put my 30 finger down. So I'll put my ring finger down. This is sine down here. This is cosine here. So if we're doing tangent, what do we have to do? What was tangent yesterday? Sine over cosine. So we have to use both sets of fingers. So we've got to go square root of one finger over square root of 3 fingers, because that's sine over cosine, which square root of 1 is what? 1, so it's the same number. 45, you'd put the 45 down, you'd say square root of 2 over square root of 2, which is 1. You did 60, you'd say square root of 3 fingers over square root of 1 finger, all right? So how is tangent different on your fingers? You've got to use both sets of fingers, all right? Because sine was one set, it was the bottom set, cosine was the top set, but now tangent that we discovered yesterday is both, all right? So we could have filled this table out using our fingers as well, all right? Everybody okay with that? Just trying to keep that connection with you as you're going. What I'm going to do right now is I'm going to take these values that we have here, and let's go to our graph paper that you picked up on the way in, and we're going to go graph it. Okay? So on our x-axis, what are we going to put on the x-axis? What's the x part of our table?
Cosine. So, x.
The x. What's the x? Look at your tables that we just made from yesterday.
Angles.
The angles go on the x. What's going to go on the y? Tangent, which is all my slopes.
Which
all right?
do we put this on?
Either one. You got 4 to choose from, so put it on one of them. All right? So I'm going to put my angles here. Now, how are you going to do this? Probably not going to count 1 degree, 2 degrees, 3 degrees. Can we do it in radians? Sure. How many of you like really radians? What I figured. All right. Yeah. Checking around to make sure that you weren't the only one, huh? All right. So degrees is probably easier to do. How would we label this in degrees? What would you do? Maybe 15s?
Go up by 15.
Or even
30.
30s. All right. I'm going to do 30s because 15s is not going to quite get it. All right. So I'm going to go 30. So I'm going to go 30. 60, 90, I know what you're thinking. You're thinking 45, correct? So I gotta handle that. We'll do that here in a second. 120, 150. You don't have to label all these. All right, you can label whatever it is that you need to be able to do that. You just label 30s for all I care. Okay? All right. Where was the first point? What was the first point in our table? 0, 0. All right? So the first point on our table is 0, 0. The next one was pi over 6, or 30 and 0.577, so just a little bit over half. Okay? Now this is the point that's kind of weird because this one's 45. Where would 45 go on my scale? In between 30 and 60, so like 1.5 on the graph. So halfway there and go to 1. 60 was 1.73, so it's up there at the top of the graph that I have. Okay. Now, here's the peculiar thing. What happens at 90? It's undefined. Okay? Undefined means it doesn't have a point on the graph. Normally when we're graphing, what do we use? What do we do when it's undefined?
Add like a dotted line.
Add like a dotted line. What do we call that?
Asymptote.
Asymptote. There's an asymptote here. There's a hole in the graph, or there's an asymptote. In this case, there is an asymptote. So I have an asymptote right there. The graph breaks apart. It doesn't work for 90. Now when I keep going, when I go to 120, I'm at negative 1.73. At 135, I'm in the middle. I'm at negative 1. At 150, I'm at negative 0.577. And then at 180, I'm back to 0. So that's a graph of what we've done so far. Now I'm going to keep going just to see a little bit more. If you think about this from what we discussed yesterday, we're graphing slopes, correct? These had a positive slope, so we're above the x-axis. The ones in the second quadrant had negative slopes, so we're below the x-axis. What happens in the third quadrant? What kind of slopes are those? Back to positive again. And so what's going to happen is all these are going to get repeated over here. So this one's going to be 0.577. The next one's going to be 1. The next one's going to be 1 point there. And then I'm going to have at 270, I'll have another vertical asymptote at 270. Then the last little bit would be in the fourth quadrant. What's the slope in the fourth quadrant? Negative, so it's going to repeat all these negatives. So I'm going to have a negative there, and a negative there, and then I'd be at 0. Okay? My graph right now has a lot of points, so let's connect those points. Okay? So if I were to connect the points, the graph looks like that. Graph looks like this. And the graph looks like this. So we had sine and cosine graph, which were they very similar? Yes. Now we have tangent. Is it similar?
No.
It looks quite a bit different, correct? All right. What are some things about it that look different to you right now, just off the top? It looks quadratic, close. I'm not thinking I'd pick quadratic, but there is another function that does resemble. Anybody remember the function that this is? This looks like a function that we've done previously.
Oh, the I know what this is. It's not
Log?
Cubratics, or the cube, whatever.
Quadratic. Sorry,
Yeah,
you
cubratics.
just get it all. That's a nice inclusive term, quadratics. I like that. It's a cubic graph. All right? It looks a little bit like a cubic graph that we did, except it's not just one. What is it? Looks like it's a multiple cubic graphs on there. All right, so it's kind of got that same kind of nature. It's a little bit different. What else is different about sine and cosine and tangent? Did we have any asymptotes in sine and cosine? Those graphs were nice and continuous. That wave never broke. All right, it always was good. All right, and so let's talk about this. Let's discuss the domain and range for this graph right here. Before we discuss that, I want to do one other thing. I want to use this graph right here. Well, let's go put it in our calculator also. So grab your calculator. I'm going to go to on, and I'm going to go new, and I'm going to go add a graph. Okay? On new, I'm adding a graph. I'm going to go trig, and I'm going to say, okay, let's go do the tangent and of x. Now, depending on what my calculator's in, depends on how much I'm going to see. If it's in radians, I'm going to see quite a bit. If it's in degrees, I'm not going to see a whole lot. I'm going to have mine in radians, and I'm going to graph. So there's the same picture of what we just graphed. It's just graphed it a lot more. So we'll use that to help us as well as we answer some of the questions. Okay. So going back to it, domain and range. What's the domain for this graph?
All real numbers except multiples of 90.
Okay, all real numbers except the asymptotes, right? And so the 90 is the first one. When you say multiples of 90, a multiple of 90 would be 180, right?
Oh.
So I think you're on the right track. We're gonna evaluate it again here in a minute, but you're on the right track there. And so we would say the domain is all real numbers except for, I'm gonna say except for 90 and except for pi over 2 right now. That's the same number. So if we're dealing with degrees or radians, okay? But 90 is not the only time it fails. It fails at 270, and it fails again. If I were to keep going around the circle, remember this idea is that beacon of that lighthouse yesterday. So we have that lighthouse, and that beacon's going around, and it doesn't just go around once, it's going around continuously. All right? So all real numbers, but I don't want to list all of them. I'm going to give you another way to list them here in a second. Okay? We got to develop something else. But a whole lot of numbers work, but there's a couple numbers that don't work as well. All right? What's the range? All real numbers. How far up? How far down? Forever, right? You can make whatever slope that you want. We saw that yesterday. We had 80 as a slope. We could make even a bigger one or even a smaller one if we wanted to. So all real numbers. Okay? Is this graph periodic? Got a couple yeses. What does it mean, the periodic? What is the kind of definition there? Say again?
Happens all at the same time.
Have the same, there's certain points that happen at the same time for multiple times, you just kind of keep on going, all right? It is periodic. It's repeating kind of like sine and cosine did. It's doing it a little bit differently, but it's still repeating, all right? So if they were to ask me, is the tangent graph periodic? I would say yes. Okay, is it periodic? Yes. Now, the follow-up question, if it's periodic, then what is the period? 180 degrees. Or, how would we say that in radians? Pi. 180 degrees or pi. So, I noticed that, hopefully you noticed that there and there. Those 2 points are the same point. Correct? They are 180 degrees apart. They're pi apart. How else could you do that? The asymptotes. You could look at the asymptotes. How far apart are the asymptotes? Because we see them repeating. They're 180 degrees apart as well. There's 6 spaces on the graph, which each one's 30, so that's 180 degrees. All right? So it is periodic. Now, using the period, since it's 180 degrees, now I can go back to the domain and I can write a better equation. All right? So the domain is all real numbers except x cannot be 90 plus 180 degrees times n. Now, what do I mean by that? Well, the period is 180 degrees. So if I start at 90, if I go 180 degrees one time, that one's not going to work. I could go a second time, I could go a third time, I could go a fourth time. So this n means however many periods that you want to go out. You want to go out 3 periods? 3 times around the graph, that's fine. Could n be negative? All right? And so that would be an easier way of stating it than having to list all of them. By the way, how many asymptotes are there in this graph? An infinite amount. I don't want to list them all. Okay? Everybody okay with that? Now, if you were doing this in radians, we'd say we can't use pi over 2 plus what? Plus pi n. All right, so that's how I would list that in radians. Everybody okay with that? Little bit different because we got a little bit different graph. Okay. Now, you can continue taking notes on this sheet. You can take notes in your book. I don't care. Whatever you want to do. All right. But I can write this equation in this general format like this, just kind of like what we did with sine and cosine. What would the A value represent? What has it? It's represented radius, but we're not really measuring the radius here, right? We're measuring the slope. Okay, what were you gonna say? Okay, what'd you say? Amplitude. That's what it's meant, right? We said this is the amplitude, but this graph looks a little bit different, though. Correct?
What the slope is?
All right, because this graph, I don't really have an amplitude. When we're thinking about like waves, we got a high point, we got a low point. We don't really have that here. What's another name for that amplitude or another name for that A value that we were putting out front? Just in general. Vertical stretch or compression. Vertical dilation. All right. So it's kind of back to where vertical dilation probably is a little bit better characteristic of that than the amplitude. Okay. What does the B value do? It tells us the period. It tells us how the period is affected. The B value affects the period. Same thing it did in sine and cosine. It affected the period there. Now, it was not the period, but it affected the period. I gave you a little formula on the test to help you with this, all right? Because there's a formula that connects this. What's the formula that connects the B value with the period? Good. Period is equal to 2 pi over B, except on this one it's going to change slightly. Because what is the period for a tangent? 180, or pi. So same kind of connection, but my normal period for a tangent graph is pi instead of 2 pi. So my formula gets adopted and changed just slightly, all right? Everybody okay with that? So if I know the b value, then I could go find. All right, c value. What's the c? Moves the graph left to right. It's still my phase shift. Okay? This is still my left and right. And the d value? That's my up and down. It's kind of my midline still. Alright? On the one of the tests, it called it a vertical translation, which is my up and down. If you were to look at the graph right here, where's the middle of the graph? Is the x-axis right here? There's the middle. You see, that's kind of where the graph is kind of changing directions. All right? We called that an inflection point when we were discussing cubic graphs. Right? Told somebody one time that this looks like a heartbeat monitor or something like that. Somebody told me that was more medical than I am. I don't know. Said, no, if your heart looked like that, you would die. So I was like, okay, whatever, but I hope that's not the case. All right? And so, but it kind of looks like that you would see a heart monitor. It kind of just keeps going. Oh, that's my take on it. You don't want me to care for you, I promise. All right, go see a real doctor. Okay? All right? You there? Here's what I want to do. I want to graph one problem using these transformations. So use another graph on there. We're going to go f of x equals 2 tangent of 1/2.
Are we using all of these graphs?
No, we're not going to use all of them.
What's the other paper?
Oh, we're going to do that here in a minute. All right, so we're going to go graph this one together. F of x equals 2 tangent of 1/2 x minus 1 minus 3. Okay? This time, the way that this is written, what we're going to do is, actually, I probably should write it differently. That's okay. We'll do that for now. All right? We'll talk through this as we go. So, where does a tangent graph normally start? Where do we start on that previous one? 0, 0. So it normally starts at 0, 0. So if that's the case, how is this one going to move? Right 1 and down 3. So we would move right 1 and down 3. 1, 2, 3. Now, I know the scale says those are halves. I'm going to count them as wholes. If not, I'm going to be off the graph. So we're going to say right there, that's going to be my starting point. Okay? What is the period for this graph? I have to go use my formula. All right? So the period would be pi over b. So we're going to go pi over 1/2. Because the b value is 1/2. I'm going to keep, change, and flip. So 2 pi is going to be the period for this graph. So the period changed. It's not my normal one for a tangent. It's going to be this one. Now, 2 pi is another way of saying what? 360. All right? So I'm going to do a little conflicting here. I don't have enough deal here to graph 360. Actually, let me just graph 2 pi. That'll match a little bit better. 2 pi is how much? 6 and a little bit more, right? Now, here's the thing. This is the middle of my graph. When will I see the middle of my graph again? In 2 pi. So I'm going to count. 1, 2, 3, 4, 5, 6, and a little bit more. That's where I'll see that again. Okay? Same thing, I could count it this way if I wanted as well. I could go 1, 2, 3, 4, 5, 6, and a little bit more. So those would be the middle of my graph. The next thing that I would do is I would draw my asymptotes. Where are my asymptotes going to be? Did you notice? Say again? they're gonna be 3.1, right? They're gonna be right in the middle of those 2 points there, okay? So if I were to look here, these are basically like 6 away from each other, pretty close. So about 3, 1, 2, 3, and a little bit more, there's gonna be an asymptote there. So that's kind of in the middle, all right? It's nice and kind of symmetric as we're going. So that's in the middle there. I would have another one in the middle here. So I kind of have that set up. And then the last point on here is, if you remember, if you look at this here, the best point on the table that we were using were the 45s. 45s gave me a slope of 1. This 45 gave me a slope of -1. Those are really good points on the tangent graph. So if I was going to use those points, that 45 point that we're doing there, that point is in between the two things here. It's between the middle point and the asymptote. And I'm going to go up normally 1, but this has a vertical stretch of 2 on it, so I'm going to go up 2. So I'm going to go in the middle, and I'm going to go up 2. I'm going to go in the middle, and I'm going to go down 2. Over here, I'd go in the middle, and I'd go down 2. Over here, I'd go in the middle, I could go up 2. All right, so there is a picture of that graph. Okay? Now, you could draw more of it. I'm not going to ask you to draw a graph on Friday or anything like this, just kind of introducing this concept, kind of tying it back to our sine and cosine. We'll do some more of this next year in IB and in pre-cal. Okay? All right. So what I want you to do right now, I want you to turn your attention to the other sheet that you picked up on the way in. I want you, because we're kind of combining what we did yesterday and what we're talking about today, I want you to go look at question A and question B. I want you to see if you can tell me question A, answer question A, and then I want you to go draw me question B. All right. So, how do you find the slope of terminal ray shown in the figure? How do you find that slope? Sine divided by cosine. Good. There's a shorter way though too. That would work. Tangent. All right. You knew either one of them. All right. So you could do sine of 0.8 over cosine of 0.8, or the shorter way is to do tangent of 0.8. Now, either one of those two would have given me the correct answer. if you had your calculator in radians. It's gotta be in radians, because that's 0.8 radians, all right? So help me out, when you put that in the calculator, what'd you come up with? 1.0, I think it rounds to 3, right? 29, something or another? All right, let's do that. Let's go 1.03. If you wrote 1.296 or whatever, that's fine too, okay? Now, it asked me on part B to sketch an angle whose terminal ray has the same slope as the angle shown, but not coterminal to it. All right? So where would be the slope? Where would the terminal ray be? The terminal ray is the one that's moving around the circle. Where would that be? Quadrant 3. If I were to extend this line right there, I'm in quadrant 3. Does that have the same slope as that line? Still positive. Okay? So I've drawn that. Now, I'd like for you to determine the angle of that right there. All right, so think about that. How do you find the angle measure for that one right there?
I think I knew rejoicing if I ran a 4 now. Really good. Yeah, like I know those are bad, but tiny. No, for me too. Okay. And that one
They're so
round up.
close, they're so close.
Yeah, and then you get free test.
They could go 70 and 1.
Like on a scale of 1 to 10, on a scale of 1 to 10, how many is that?
That day, and I did that.
Oh, yeah. So, but I think if you get 100 all of these times, which you can, yeah, then you'll.
All right, here you go. What do you think? How do you find the angle in this quadrant right here? You add pi. Now, does that connect? What is the period of tangent that we just worked on? 180 or pi. And so the tangent's the slopes of the line. That slope repeats itself here, and it repeats itself in the period, which is 180 or pi. Now, since I'm dealing with radians here, you would do what? 180 or pi? Pi. All right? So to do this, I would say 3.14 plus 0.8. And so that's 3.94 would be that angle measure. Everybody okay with that? Is that what you got? You could have converted to degrees if you wanted to, but that's a lot more work. So part D says, what's the relationship? They differ. Those measures differ by the period, which is pi or 180 if you had an example that was in degrees. Okay? All right, last problem here. What is the measure of an angle whose terminal ray is the opposite slope? It's missing the word slope there. What is the measure of an angle whose terminal ray is the opposite slope of the angle in the figure? See, we went the opposite slope. So what kind of slope do we want? Negative slope. So draw where the negative slopes are.
Can we just put the radians in negative to show that we're going the other way?
You could do one of those that way, yeah. I don't know that you can do all of them that way.
I took a picture of this.
It'd be the same
Our
jump
bracelets,
going negative.
because we have matching ones like this, and matching ones like this, like these two. And then I got a blue bracelet, and she had a red bracelet. This is cute.
All right, so let's discuss it real quick because we're close to being out of time. All right, so which quadrants would have the opposite slopes? 2 and 4. So we're talking about this and we're talking about this. All right, what would this angle measure be from there to there? Okay, how'd you get that? Okay, added or subtracted it? This is 0.8. So if we went pi minus 0.8, then we would get that angle. Right? Pi, right here, minus 0.8, then we would get that angle. Alright? How would you come up with this angle right here? Pi minus 0.8 was one of them. What'd you say? Somebody said it. I could do 2 pi minus 0.8. Would give me that one. So I'm starting at 2 pi at minus 0.8. This is going back to the reference angles that we referred to. Okay? How's another? There's one other way that you could say this one. You could say 2 pi minus 0.8, or you could just say a negative 0.8 radians, correct? Going the other way around the circle. All right. Got a couple more minutes left. Make sure your name's on that. Let's put that on my desk. Should be a nice, easy day to grade for the day. I don't want the graph paper. I just want this sheet right here.